Okay. Perfect. How things are going? Everything is fine? Okay. I just wanted, before starting, to clarify the schedule for the next lectures. And for the next week, you know that it's the week before Easter. So we will have lecture on Tuesday only, because on Thursday and Friday, the lectures are not suspended, are not given. So basically, for next week it's clear. And I also would like to anticipate what happens a week later. And so, we don't have lectures on Tuesday, April 7, because the university is still closed, so we have no lectures still. And therefore we will have lectures on Thursday, April 9, and Friday, April 10. And most likely, I will ask you, I think I can say this already now, on Thursday, I will lecture during this week, so the next, all these lectures will be given by me. On Thursday, April 9, please bring your PC, okay? And the week later, I also would like to anticipate that, just 1 second, yes, I will lecture on Tuesday, April 14, and there will be no lectures on Thursday and Friday, April 16 and 17, because we are all attending an international conference, and me and my colleagues, so there will be no lectures. And then everything moves forward smoothly. I think I confirm to you that basically, I think at the end of April we should be able to finish the lectures. And of course, the exact date in which I will close the lectures will be communicated later. Maybe end of April, maybe just the first week of May. It depends. I still have to check how many hours are missing, and also you have to check the progress of the subject. And also I would like to confirm to you that as soon as I close the lectures, I will give you the opportunity to take the exam. And in a date that you will tell me, I'm flexible. And of course I cannot record any mark until June 6, so you have to just trust me. Okay, you take the exam, I take a note on a sheet, and if nothing happens to me, so you have to cry for me that everything goes forward. But my health is quite fine so far, so you have to trust me, and then at the first, I will fix an appeal as soon as the official date allows it. So it will be, I think, around June 10. As soon as I can, I will fix an official appeal, and you will have the opportunity to take the exam during the official appeal if you wish, if you didn't take it before. But in any case, I will register all the marks, I will record all the marks in the system during the official appeal, soon after the official appeal. Is it clear? So you will take an informal exam, not informal, you will take the exam when you want, in May, if you wish, and then it will be registered in the system as soon as the official appeal is over. Is it clear? Okay, perfect. And for the date of the exam, I am flexible, but let me say that as soon as we have clear when the lecture will finish, we can take a decision. Just let me know if you are in a hurry, you can just ask me, but I think that around April 10, I will be able to tell you the complete schedule of the lectures and the dates of the exams, and the unofficial and official ones. Okay? For any question, please don't hesitate to refer to me. You are not many students in this subject, so for the exam, I am quite flexible. I don't need to stick on, to stick very strictly on fixed dates. Okay. So, you started to learn something about the decision theory and in particular about Lagrange multipliers. So, if my colleague used the symbols that are in my slides, basically you learned how to write the Lagrangian for a given decision problem, and you wrote it in this way. The Lagrangian is indicated by the symbol L. It depends on a decision plan, which is a vector of decision variables. If something that I'm saying is not clear to you, just ask me questions, please. So it depends on a decision plan X, which is a vector of decision variables. Typically, in our cases, these decision variables are water allocation to users. And the Lagrangian also depends on a multiplier lambda. And basically the Lagrangian is written in this way. There is a benefit function which depends on x, which is penalized by a penalty. So the Lagrangian is obtained by summing the benefit function, and NB means net benefit because we assume that this is a net benefit. We don't have to remove costs, taxes, etc. It's already net. So the Lagrangian is obtained by summing the benefit function, which is penalized by a negative term. At least we sign it with the negative sign here. And the negative term, it's depending on a constraint. It's depending on a constraint, and the constraint can be in general form written in this way. So there is a function which I call G of the decision plan, again, minus a constant. And in the case of, let me make an example, which I think you made already. And the example could be an example where decision plan is given by three decision variables, x1, x2, and x3. And let me make the constraint in this way. G dx maybe is equal to x1 plus x2 plus x3 minus q. And basically, in this example, again, the decision plan is given by three water allocations, and the constraint is given by the fact that the sum of these three allocations shouldn't exceed, or let me say, should be equal to Q, which is the water flow that we have available. So basically, again, what is the constraint? I have a water flow, which I indicate with the letter capital Q, and the sum of the three allocations should be equal to this available flow. So let me assume, for instance, that the water flow is 10 liters per second, because it's the water that is given to me by the aqueduct. And therefore, of course, the sum of the three allocations shouldn't exceed, or let me say in this case, it should be equal to 10 liters per second. This is an equality constraint. It's an equality constraint. I just would like to anticipate that in general, our constraints in water resources management are inequality constraint, because usually we impose that the sum of the allocation doesn't exceed water availability. We don't impose that the sum of the allocation is equal to water availability. We don't impose that we distribute all the water. We impose that we don't distribute more water than available. This is our constraint usually. We are happy if we can save water. So if we distribute less water than Q, we are happy. What we can't do is to distribute more water than available. So this is an inequality constraint. For simplicity, now we are studying a problem where the constraint is an equality constraint, but this is done for simplicity. So this is a premise that I wanted to make you, because I'm not sure if my colleague already explained to you why, in this case, we adopt an equality constraint. You didn't, she didn't explain to you how to set up an inequality, correct? She didn't. Or she did?
She didn't.
Didn't. Okay, perfect. So in this case, again, the reason why I consider an equality is for simplicity, because you will see that the inequality is a bit more complicated, not much more, but it's a bit more complicated. Okay, so let me make this example then. And then, if I make this example, the Lagrangian, let me keep the benefit function very general, but let me substitute the constraint in this form in this general relationship. So the Lagrangian can be written as Lx lambda is equal to the net benefit, depending on the decision plan, minus lambda, which multiplies x1 plus x2 plus x3 minus q. Okay, this is what you did basically. Now you know how to solve this. And again, let me focus on the physical meaning. The physical meaning is very simple, it's like a trick. Basically, if you want to introduce a constraint into a benefit function which you are trying to maximize, if you want to introduce a constraint when you maximize this benefit function, what is the trick? The trick is to introduce a penalty. And the penalty decreases the benefit, you see a minus here, when the constraint is not satisfied. It's a very simple trick. So you look for the maximum of a benefit function, but you have a constraint, and if you want to account for it, the trick is to penalize the benefit function when the constraint is not met. And therefore, in this way, you avoid to look for solutions that are not possible. Because of course, if you distribute more water than available, you violate the constraint, but your benefit would increase. So you could not realize that you are violating the constraint and could get to a solution which corresponds to a higher benefit, which is not possible because the solution gives more water than available. And then you penalize the constraints. It is really like a trick. Of course, you understand that the value of lambda must be well selected because the penalization should have a correct amount. If you penalize less than optimal, so if you reduce the value of lambda too much, then the penalty could not be effective. But if you penalize too much, then you could exclude solutions that are still possible. So basically, of course, let me make a trivial example. If you increase lambda too much, you could get to a negative value of the Lagrangian for any solution, which is not feasible. So you cannot penalize, you cannot increase lambda by bringing it to whatever value tending to infinity. So, of course, you need to identify the correct value for lambda, and you know how to do that analytically, because you got to a system of equations that give you not only the value of the x, but also the value of lambda. So you know how to analytically find the correct value of lambda. But from a physical point of view, let's forget the analytics. From a physical point of view, you understand that it's important that this lambda is there, is not zero. because you need a penalty. When you have a constraint, you need a penalty. But also cannot increase too much, because the penalty should be a proper penalty. Okay, now, what is the solution to this problem? You already learned it, and the solution is given by the fact that you take the partial derivative of the Lagrangian with respect to x, to each x, lowercase x. And you take the partial derivative of the Lagrangian with respect to lambda, and you equate them to 0. Perfect. Now, let me write them here. Or let me write here the partial derivative with respect to xi. So basically what I can write is that the partial derivative of L, which depends on x lambda, with respect to xi, where I is varying from 1 to 3, this is equal to the partial derivative of ndx with respect to xi minus the partial derivative, or let me bring lambda out, lambda times the partial derivative with respect to xi of x1 plus x2 plus x3 minus q. Sorry, I used the frame of the blackboard to write q. Okay, this is something that you did on Tuesday. Given that I don't like the fact that I have written here, let me rewrite this on the top of this blackboard. I am just rewriting, so the partial derivative of L x lambda with respect to xi is equal to the partial derivative of nb x with respect to xi minus lambda, the partial derivative with respect to xi of x1 plus x2 plus x3 minus q. Okay. This is the partial derivative that you equated to 0. Okay. Now, of course, in my example, where I have 3 decision variables, I can write 3 of such partial derivatives, because I can take the partial derivative with respect to x1, with respect to x2, and with respect to x3. Now let me make one consideration. And the consideration that I want to make now is the following one. I already told you that lambda must assume a given value. And the given value, we already discussed the fact that you, from an analytical point of view, you know how to compute it. But from a physical point of view, I also told you that this value of lambda shouldn't be too low and it shouldn't be too high. Now, I want to make some reasoning to prove to you that lambda indeed takes a precise value that has a very precise physical meaning. So you know that it takes a precise value that is given by an analytical solution. But let me tell you and prove you what is the physical meaning of the lambda value. Because it clarifies the fact that the penalty that you give to the benefit function shouldn't be too high and shouldn't be too low. And it must be a very well-defined value of penalty which has a physical meaning. And this is what I want to discuss with you now. And I want to base this discussion on this relationship, this partial derivative that you already know. You already know that you have to impose this condition for each of the three partial derivatives plus the partial derivative with respect to lambda in order to identify your solution. So I want to start from here. This is a relationship that you already know. And now let me take these three partial derivatives with respect to xi and let me multiply each of them by the related dxi, which is the infinitesimal increment of the related decision variable. So I want to take each one of these partial derivatives, multiply it by the related dxi, and sum them. And I want to sum them. So let me try to formalize this operation that I want to make. And basically what I can do is to compute the sum for I varying from 1 to 3 of the partial derivative. And therefore I write, sorry, let me take, I am running out of chocolate. I still have some reserve. Partial derivative x of L x lambda with respect to xi multiplied by the xi and then I can write it by considering this right-hand side term. So basically, I can write that this summation is equal to partial derivative of the net benefit function nbx taken with respect to xi dxi, and here I have a summation from I equal 1 to 3 minus lambda partial derivative with respect to xi of x1 plus x2 plus x3 minus 2, sorry. In the xi, there is a summation here. Summation from I equal 1 to 3. And this is again equal to 0. Why is equal to 0? Because each time I multiply 0 times the x1 plus 0 times the x2 plus 0 times the x3. So it remains being 0. This is just a mathematical transformation that I did of this relationship that you already know. I multiply each partial derivative again times the xi and sum it. I took the summation. So analytically, you can understand that it remains satisfied. Okay. Now, if you look at what I've written, it's quite clear how to write it in a very simple form. And let me delete the first relationship here, and let me write on the top of the blackboard. Now, what is the summation? The summation is the summation from I equal 1 to 3 of the partial derivatives of the benefit function times the xi. This is basically the summation of the three partial derivative times the xi. It's the finite increment, the infinitesimal increment, total infinitesimal increment of the net benefit. Because if you take a function of x and you take all the partial derivative with respect to each xi, multiply for the infinitesimal increment xi, you take the infinitesimal total increment. So if you have a function, basically what is let me write it in general form. If you have a function f of x and y, very generic function, how would you write the total increment f xy? Simply by taking the partial derivative of f with respect to x in the x plus the partial derivative of f with respect to y in the y. This is a relationship that the total increment the total increment, this is a relationship that you know from your background in mathematics. If you have a f in xy, you take the partial derivative in x times the x plus the partial derivative in y times the y, and you get the total increment. And this is the same thing that I did here. So this is the total increment of the benefit. Okay, and then what do we have here? Here we have minus lambda, which multiplies, let me write this summation. Lambda, I can bring it out of the summation because it's a constant. So, what is the result of the partial derivative with respect to, let me say, x1 of x1 plus x2 plus x3 minus q? It's just 1. So if I take again, the partial derivative of x1 plus x2 plus x3 minus q with respect to x1, it's 1. So basically here I can write 1 times the x1 plus 1 times the x2 plus 1 times the x3. Good. But basically here I can write minus lambda dq, because the x1 plus the x2 plus the x3 is the q. Because q is equal to x1 plus x2 plus x3. Then I can write here my final relationship that I wanted to derive, which is very simply lambda is equal to the total derivative of the net benefit depending on the decision plus plan x with respect to water availability. This is what I wanted to achieve. And now let me explain to you that this relationship has a very precise physical meaning. what is the Lagrangian, and I am rewriting it. Remember what is the Lagrangian? The Lagrangian is given by, I'm rewriting, Lx lambda is equal to a benefit function minus a penalty. Okay, perfect. Now, what does it mean from a physical point of view that lambda is equal to the total derivative of the net benefit with respect to water availability? What does it mean? Let me make you an example, and let's suppose that I have one decision variable only. So, let me make a graph where I have one decision variable x on the abscissa and the net benefit and the x in the ordinates. And let's suppose that your benefit function behaves like that. And let's suppose that at a certain point here you get to a value of x star, which is your q. You get a value of x, which is your q. So you get to the constraint. Okay? So your benefit function gets this constraint, but let's suppose that you don't know it. Let's suppose that you are just finding now the maximum of the benefit. And therefore, if you ignore your constraint because you don't know it, this benefit function would continue to increase. And therefore, you would continue to look for value of x which are not feasible. And then you have to introduce a penalty. And what is the amount of this penalty? Let's suppose that you go for a quantity. You go forward for a quantity dq. So you go forward for a quantity dq, and then you get an increase in benefit d and b. This is impossible. So what should your penalty do? Should neutralize this additional benefit d and b. Neutralize. And how can I neutralize it? By giving to lambda this value. So if I give to lambda a value that is equal to the increase of net benefit divided by dq, then I am done, because the penalty is correctly attributed. Because lambda here would be additional net benefit divided by dq times dq. And therefore, your Lagrangian doesn't increase. The net benefit would increase here, but the Lagrangian remains flat. Because the penalty is equal to the increase in benefit that I would get if I violated the constraint. So now we know two meanings of lambda. One is analytical, the other one is physical. This is a demonstration that I could ask you at the exam. The question, Lagrange multiplier, is very popular in my exams. Usually it's my first question. Not for everybody, of course. But let me say that usually when I make my exam, usually I make the exam to two people, and therefore for one of them the first question is Lagrange multipliers. Just keep in mind it, because I think it's extremely important. It's the basis for decision theory. And also this demonstration that the penalty is well assigned, the analytical penalty has also physical meaning. It's, I think it's important. There is one other thing that I wanted to ask you. Did my colleague discuss with you the necessity to check the boundary conditions for the solutions or not? Did she speak with you about boundary condition? Okay, this is very simple, and I want to discuss with you what it means. So basically, at this stage, you know how to find a solution according to the Lagrange multipliers for equality constraints. Okay, that's fine. And once that you find the solution, there are a couple of additional checks that you need to make, because the Lagrange multiplier gives you an analytical solution, but you have to check that this analytical solution has a physical meaning. And let me discuss with you with these two checks. The first one is very trivial. You must check that you got to a maximum of your benefit function and not a minimum, because the method of the Lagrange multipliers identifies maximum and minimums. So you have to check that you got to a maximum and not a minimum. This is very simple. You compute your benefit for the solution that you find, and then you check that it's indeed not a minimum, which is very simple, because, as I said, you find a solution X, you compute the benefit, and then you change X by meeting the constraint, you give a whatever value, and you check that it's lower. Okay? This is very simple. So let's suppose that your solution is x1 equal to 10. Okay, you try x1, you compute the benefit for x1 equal to 10, and then you try for x1 equal to 8. And you check that the benefit is lower for 8. If it is higher, it means that you got to a minimum, because there are only two alternatives, either a maximum or a minimum you found. And in these cases that we discussed, it's clear that you get to a maximum, but these cases are simple.